Today I want to talk about two new types of nuclear reactions. We've talked about radioactivity before. Radioactivity, a spontaneous process, a natural process in which one nucleus decays into something else because of some instability caused by too many protons, too many neutrons, caused by whatever. One nucleus spontaneously, naturally, randomly decays into something else. In all types of radioactivity, we get transmutation. We get the conversion of one element into another element. Well, we can have other types of nuclear decay as well, other types of transmutation as well, that result in the conversion of one element to another. And today we're going to talk about a couple types. Specifically today, I want to talk about nuclear fission and nuclear fusion. Nuclear fission is a nuclear process in which one heavy nucleus splits into two lighter nuclei. You can see here in this example that I have listed here that uranium-235, which is a heavy nucleus, splits up into krypton-92 and barium-141, which are two lighter nuclei. Now, the reason that this takes place is because we've bombarded uranium-235 with a neutron. The neutron briefly, ever so briefly, fuses together with the uranium-235, which makes it more unstable than it already is and causes it to decay into two smaller things. Now, these two smaller things, krypton and barium on the right-hand side, we can get other combinations. Krypton and barium are not the only possibilities. They just happen to be the most common ones that we see written out. There's lots of possibilities, though. When we bombard uranium-235 with a neutron, it will split up into two lighter nuclei, and that's what we call nuclear fission, when one heavy splits into two lighter. There is a neutron on the left-hand side, and there is, as you can see here, three neutrons on the right-hand side. Can you tell me why the requirement to have three neutrons on the right-hand side? Like, what is it about this equation that makes it necessary to have some neutrons produced on the right-hand side? Specifically, three neutrons produced. Spencer? Not too many electrons, no. Cameron, what were you going to say there when you raised your hand? Yeah, it's just to balance it, right? We have, on the left-hand side, 236 as our mass number and 92 as our atomic number. We have to make sure that on our right-hand side, we have 236 and 92 as well. If you look at krypton and barium, it would work out to be 233 and 92. Well, that means we're missing three neutrons. So we have to add on three neutrons in order to make that work. Does that make sense? Plus, we have some energy released as well. You guys know that in a nuclear fission reaction, we're going to get some energy released, whether that's the fission reaction of a bomb, of a nuclear bomb, or whether it's the fission reaction that takes place in a nuclear power plant to generate electricity, we're going to get energy released. If we look at this, it looks like there's a ton of energy produced there, eh? 200 mega electron volts. Anytime you see mega, it must be a lot, right? That's actually not a lot of energy. 200 mega electron volts is probably about enough energy to move a speck of dust. So how is it that we blow up a city? Or how is it that we generate enough electricity to power a city when the energy that's released here is the energy that moves a speck of dust? Brandon? Yes, you get a whole bunch of them happening at the same time. But it's not just as simple as, well, you want a whole bunch of them to happen. Let's bombard a whole bunch of uraniums with a whole bunch of neutrons to get a whole bunch of these 200 mega electron volts taking place. In order to sustain this, in order to get enough energy to blow up a city or to power a city, we need what's called a chain reaction. A chain reaction is when the product or products of one reaction cause more reactions. We need a neutron to be absorbed by uranium-235 in order to cause 200 mega electron volts of energy to be produced. Well, you can see in this reaction that in addition to the energy that's released, we also get 3 neutrons. So if we engineer this properly, and it's not a simple engineering feat to do this, but if we manage to engineer this properly, we can cause these 3 neutrons to react with 3 more uranium-235s, which will cause 600 mega electron volts of energy to be released, and 9 neutrons. And if we engineer it properly, then we can cause those 9 neutrons to react with 9 more uraniums, which causes 27 neutrons, and 81 neutrons, and 243 neutrons, and so on, and so on, and so on. So within a small fraction of a second, you've built this uncontrolled chain reaction, which results in an exponential, the energy, that 200 mega electron volts, growing exponentially. It grows so fast that it would typically, that is, if it's uncontrolled, blow itself apart within a fraction of a second. You know that in 1945, when the Americans dropped the atomic bomb on Hiroshima, they used about 50 kilograms of uranium. 50 kilograms of uranium. And there was only about 3 to 5 kilograms, we don't know exactly how much, but about 3 to 5 kilograms that actually exploded. The rest of it didn't explode. But they knew that was going to happen. That wasn't a surprise. They knew that most of it wouldn't explode. The reason that it didn't explode, and the reason that it was predicted, is because this explosion grew so quickly that the bomb literally blew itself apart, and therefore was no longer engineered properly for the neutrons to be absorbed by the uranium-235. Does that make sense? So why wouldn't they have just used 5 kilograms of uranium then, instead of using 50 and wasting 45 kilograms? Well, because without 50 kilograms, they wouldn't have been able to engineer it properly to cause this reaction to keep taking place, even to blow up 5 kilograms. Does that make sense? Essentially, if they used 5 kilograms, then it would have blown itself apart after a half a kilogram or so was used up. All right? So it happens really, really quickly. You can see that in a fraction of a second, we get this unbelievable, this astronomical amount of energy that's released, not because of one reaction taking place, but because of an exponential number of reactions taking place. Now, if this is a power plant, then we don't want it to grow uncontrolled like that, right? We don't want it to blow up. So what we do in the case of a power plant, when we generate electricity, is we take away some of these neutrons. We absorb some of these neutrons. If the reaction's getting a little too hot, we absorb some of these neutrons by these things that we call control rods. Take them away so they can't react with the reactant. If it's getting a little too cool, it's cooling down, it's not doing what it's supposed to be doing, then we take away some of the control rods to allow more of the neutrons to start reacting. All right? Now, this nuclear fission reaction generates a lot of energy. Okay, that's a benefit from it, right? Especially in the context of a nuclear power plant, it generates a lot of energy. But the downside to it, or at least one of the downsides to it, is that the products are highly radioactive. So we get a fallout after following an explosion, or we get nuclear waste following the production of electricity. The fallout would cause all kinds of things, all kinds of issues with people, right? Talked about some of those things earlier, right? Cancers, cataracts, genetic mutations. The products of nuclear waste would be, well, they'd be radioactive as well, but at least we'd be able to deal with those in a little bit safer way. Usually we end up burying them and encasing them in concrete to basically keep people from being exposed to it. Make sense? Nuclear fusion is our other type of nuclear decay that we're going to talk about today, or nuclear reaction that we're going to talk about today. Nuclear fusion occurs when two lighter nuclei fuse to form one heavy nucleus. So remember, we got one where we got a heavy splitting up into two light. We got another one where two light fuse together to form one heavy. Light plus light equals heavy versus heavy decaying into light plus light. Now you can see there's a neutron produced here as well in order to balance it out. There's also some energy released here. What's interesting about this is that we have this belief, this perception that fusion generates more energy than fission. After all, the Americans dropped two different fission bombs in Japan in 1945. In 1952, they developed the H-bomb, the hydrogen bomb, which was much more powerful than the bombs they dropped in Japan in the war, based on fusion. So we have this belief that fusion generates more energy than fission. And it does, if we compare apples to apples. But if we compare apples to oranges, reaction to reaction, the energy released in fission is actually less. In a single reaction, fusion releases less energy. But look at what it is that causes this reaction to take place. Hydrogen and hydrogen, two light nuclei, one heavy nucleus. If we have a kilogram of each, then we're going to get a lot more out of fusion. If we have a single reaction, then we're going to get more out of fission. Does that make sense? Like if you take 50 kilograms of uranium and it undergoes nuclear fission, you're going to generate a lot of energy. If you take 50 kilograms of hydrogen and it all reacts, then you're going to generate a whole lot more energy than you did from the uranium. But if you look at a single reaction, because each element that reacts is so much lighter, a single reaction produces less energy. Now, this is difficult to make take place. It's difficult to make happen. The reason it's difficult to make happen is because hydrogen nuclei are positively charged. Both of them are. Which means as they get closer together, to fuse together, what do, Brendan? Good, they push apart, they repel each other. In fact, if you look at Coulomb's law, as they get closer and closer and closer, the force of repulsion becomes bigger and bigger and bigger. It's really difficult to overcome that force of repulsion because it becomes exponentially large. Right, Cameron? So we have to overcome it somehow, and usually the way that we overcome it is by pumping energy into it, and that energy that we usually pump into it, usually in the form of heat. Energy causes these nuclei to fuse together, which produces a neutron and even more energy. And then sometimes we take a little bit of that energy to cause more hydrogen to fuse together, and so on and so on and so on. That's the process that takes place in the sun, effectively. How does it sustain itself? The sun's hot. There's so much energy in the sun, we can always get more hydrogen fusing together because there's so much energy there to do it. Eventually, we're going to run out of hydrogen, and the sun's going to burn out. It's going to get really, really cold here. But we don't have to worry too much about that because that's a long ways off. The upside to fusion, one of the upsides to fusion, is that the products are relatively harmless. You don't want to be anywhere near a fusion explosion But because the half-life of what's produced is so small, you could return much, much sooner than you could with a fission reaction and be safe. The products of a fission reaction are highly radioactive for a long, long, long time. The products of a fusion reaction are relatively harmless. All right? Now, where is it that this energy comes from? In both cases, where is it that the energy comes from? Like, how do we get this energy generated out of it, regardless of how much is there, regardless of which one produces more energy? This goes back to something we talked about a little bit about last unit. Yep. Yeah. It's Einstein. Energy mass equivalence. Remember we said energy and mass are two different forms of the same thing? We'll explain this in more detail in a few minutes, but the gist of it is this. When this reaction or when this reaction take place, a little bit of mass disappears. Why? Well, a little bit of mass disappears for whatever reason. A little bit of mass disappears. But it can't just be destroyed. It has to be converted to something. It ends up being converted to energy. It's kind of like taking an ice cube out of the freezer. You had a 30-gram ice cube. Well, a few minutes later, you have a 27-gram ice cube. What happened to the missing mass? Well, it wasn't destroyed, right? It was just converted to water. Now you have 27 grams of ice and 3 grams of water. If we add a certain amount of mass and we lose mass, well, then that missing mass just ends up being converted to energy. All right? I want to define a couple of terms here. And I want to define them in two different ways. Mass defect and binding energy. Both in the context of a single nucleus and in the context of a reaction that takes place. The definitions are going to seem different, but they boil down to the same thing. In fact, it's because of the mass defect and binding energy in a single nucleus that results in the mass defect and binding energy in a reaction. So it's one that leads to the other, one definition leading to the other definition. Mass defect in the context of a single nucleus. Now listen carefully, because this isn't going to make sense. This is going to be probably the wackiest thing you've heard this year in Physics 30. It's the difference in mass between the nucleus, you know what a nucleus is, and the nucleons. The nucleons are the protons and neutrons. A proton is a nucleon, and a neutron is a nucleon. It's the difference in mass between what makes up the nucleus and the nucleus. So it's like saying, in this class, let's say there's 30 people, and all 30 people, say, have a mass of 100 pounds for ease of calculation so I can do it in my head. So everybody's 100 pounds. We're classic grade 5ers, or 6ers, or 7ers, whatever. Whenever you weighed 100 pounds, I don't know. We're a class of 100 pounders. So if there's 30 of us, and we each weigh 100 pounds, we add up the mass of everybody that makes up the class, and we get 3,000 pounds. But when we measure the mass of the class, we find, oh, it only comes out to be 2,999.7 kilograms. We add up the mass of everybody, it's 3,000, but the total mass isn't 3,000, it's only 2,999.7 kilograms. There's a little bit of mass that just isn't there when we look at the total mass. That mass ends up being stored as energy. We call binding energy. So mass defect is the difference in mass between the whole class and the sum of the individuals in the class, or the difference in mass between the nucleus and the nucleons that make up the nucleus. Which leads to, in a fission or fusion reaction, the difference in mass between the products in the reactants, or the daughter and the parent nuclei. We lose a little bit of mass in the reaction. The products weigh less than the reactants because of the way that we define mass defect in the context of a single nucleus. So, to summarize that, we would say in the context of a nucleus, the mass of the nucleus is less than what makes up the nucleus. In the context of a reaction, the mass of the daughter, or we could say the product, is less than the mass of the parent or the mass of the reactant. Of course, it's the mass defect that leads to the binding energy. We're going to define binding energy in the context of a single nucleus is the energy that's required to disassemble the nucleus. That would correspond to the energy that would be stored as a result of the missing mass. In the context of a reaction, we'll define it as the energy that's released in a reaction. I'm going to cross off the last part of this sentence, not because it's wrong, it's not, because it's really the first part that we want to focus on, the energy that's released from the action. We'll assume that there's binding energy available after the reaction, and then this whole thing takes place. If it does, then we define that binding energy as the energy that's released in the reaction. How are you going to find it? Well, if you've got the mass defect, then all you got to do to find binding energy, either context of a nucleus or a reaction, is to say E is equal to mc squared, the mass defect times the speed of light squared. So if we go back to that fission reaction or that fusion reaction, we want to find out the energy that's released. Well, let's figure out how much mass we lose. Let's figure out what the mass defect is, and then simply multiply it by c squared. A couple little loose ends here, and we'll do an example. I want to briefly explain these units, not because I think you'll see them on an exam, but because we're responsible for them. A U, which is a symbol for an atomic mass unit, you might be familiar with that if you've taken chemistry. It's a unit of mass that's equal to 1/12 the mass of carbon-12. In other words, one atomic mass unit, and this is on our data sheet, is equal to 1.66 times 10 to the minus 27 kilograms. If you ever have to do a calculation or given atomic mass units, convert it to kilograms. Convert it to kilograms by this conversion factor. You easily say one atomic mass unit is 1.66 times 10 to the minus 27 kilograms equals, let's say, 3.7 atomic mass units equals x kilograms. And you need to solve for x. You get atomic mass units, convert it to kilograms. I'd be surprised if you have to do any calculations involving atomic mass units, but you never know. MeV per c squared is also a unit of mass. Both of these are units of mass. I would not only be surprised if you have to use that one, I would be almost shocked if you have to use MeV per c squared. I can't recall a single time in the last 23 years of me teaching Physics 30 that we've had to use MeV per c squared. But watch, this will be the one. So I'm showing you what it is, how to convert it, just in case. Atomic mass unit is easy because the conversion factor is right on our data sheet. But MeV per c squared isn't. There's not a conversion factor on our data sheet. I'd like you to take a look at your data sheet for a second. I want to show you how to figure out a conversion factor, how to come up with your own conversion factor to convert to kilograms. In the bottom right-hand corner of your data sheet, there's a heading that says first generation fermions. In a couple of days, by the way, you'll know what a fermion is. But for now, just roll with it here. Right underneath that, right-hand side, halfway down, it says an electron has a mass of 0.511 MeV per c squared. But we already know that an electron has a mass of 9.11 times 10 to the minus 31 kilograms. So let's come up with our own conversion. We would say that an electron has a mass of 0.511 MeV per c squared, and it also has a mass of 9.11 times 10 to the minus 31 kilograms. So that means that 0.511 is the same thing as 9.11 kilograms. If you had a MeV per c squared given to you maybe as a value of 1.714 or whatever, made that number up, you wanted to convert that to kilograms, then you just set up the ratio as you see it there. So nowhere in one single place does it say this equals this. But it tells us in one place that the mass of an electron is this. It tells us in another place the mass of the electron is this. So we know those two masses have to be equal. That's how we convert MeV per c squared to kilograms in the unlikely event that we ever need to do that. Let's take a look at example number 1 from your handout. It says, determine the binding energy in the following nucleus. We're not talking about a reaction here, we're talking about a nucleus. When you're asked for binding energy will always come from mass defect. So the two terms are not interchangeable. They mean something different, but the mass defect always leads to binding energy, and binding energy always comes from mass defect. So if you're looking for binding energy, you need to get mass defect first. Now remember what the mass defect was in the context of a single nucleus. It's the difference in mass between the nucleus, the whole thing, and the nucleons that make up the nucleus. So what we want to do here in this question is get the mass of the nucleons first. Get the mass of all the protons and neutrons. We have 56 protons in barium-141. Each proton from the table that you saw a few minutes ago, each proton has a mass of 1.67. Sorry, we're going to do it in atomic mass units here. You'll see why in a second here. 1.007276 atomic mass units. The total mass of all the protons combined would be 56.407456 atomic mass units. We also know that barium-141 has 85 neutrons. How do we figure that out? Mass 141 minus 56. Good. 85 neutrons. If you check that sheet that I gave you, or that I put up on the board here a few minutes ago, you see that the mass of a neutron is 1.008665 atomic mass units, giving us a total mass for all the neutrons of 85.7736525 atomic mass units. We add those up. We get 142.143981 atomic mass units. This is the mass of the nucleons. Those are the protons and neutrons that make up the nucleus. We're going to subtract from that the mass of the nucleus, which, if you look back at that page, the mass of barium-141, 140.914412 atomic mass units. So we subtract the mass of the nucleus. To get a number that's equal to 1.229569. What have I just found there? What's in red? How do I label that? Blue was mass of the nucleons, the protons and neutrons. Green was mass of the nucleus itself. So the mass of all the people in the class added up, the mass of the total class, What's in red? Alex? The mass defect. The difference in mass between the nucleus and the nucleons. Now, we don't want mass defect in atomic mass units. The good news is it's unlikely on a test that you would be given masses in atomic mass units. It's probably going to be in kilograms. We're just doing it this way just in case. If it's in kilograms, good. Skip the next step. If it's in atomic mass units, then you got to convert it to kilograms by doing this. One atomic mass unit is 1.66 times 10 to the minus 27 kilograms equals 1.229569 atomic mass units over x kilograms. That gives us a mass defect in kilograms of 2.04108,454 times 10 to the minus 27 kilograms. Now what? I calculate the mass of the nucleons. I get the mass of the nucleus. I subtract them to get mass defect. Then I convert it to kilograms. And now what, Alex? Yeah. Now it's just E is equal to mc squared. So we take this mass defect in kilograms, multiply it by the speed of light squared, and we end up getting 1.84 times 10 to the negative 10 joules. Lots of numbers in there, lots of numbers with lots of decimal places in there. It becomes cumbersome, it really does. But just try to follow the logic. If you follow the logic and you're careful, you're going to get these questions. Understand, to get energy released, binding energy, you need mass defect. How are we going to get mass defect? Well, let's get the mass of what makes up the nucleus and the nucleus itself and subtract them. And then let's convert it to kilograms. And then let's multiply it by c squared. If you had to convert that to electron volts, because that's what your answers are listed in, you could do that. Right? 1 eV is 1.6 times 10 to the minus 19 joules. Do your conversion. Let's take a look at example number 2 on your sheet, which says determine the energy released in the following nuclear reaction. So first one we did, binding energy in a single nucleus. Still going to get mass defect, multiply it by c squared. Energy released in a nuclear reaction, get mass defect, and multiply it by c squared. Just the way that we get mass defect is a little bit different. Here, we're going to look at that sheet that we had all the information on. We're going to recognize that a neutron has a mass, or see that a neutron has a mass of 1.008665 atomic mass units. Uranium-235 has a mass of 235.043930 atomic mass units. Krypton has a mass of 91.926156 atomic mass units. And again, that's on a sheet. You don't need to memorize that number. Barium is 140.914412. And this is 3 times 1.008665, because there's 3 of them, right? We add up all the numbers on the left-hand side. We get 236.052595. And on the right-hand side, we add up all those green numbers. We get 235.866563 atomic mass units. Hey, wait. The products weigh less than the reactants. Would we expect that? Yeah, it's what we define mass defect, right? Difference in mass between the products and the reactants. How do we get the value of the mass defect? Subtract them, right? It gives me a mass defect of 0.186032 atomic mass units, which I want to convert to kilograms. Here's my mass defect in kilograms, which I now convert to energy by using E is equal to mc squared. So that's not very much energy, right? But that's one single reaction taking place as well. And we know that that grows exponentially fast. So that we got an astronomical number of these reactions taking place every second. So the way we do this is almost the same as the last question. Almost. Get mass defect, convert mass defect to kilograms if it's not already there, and then multiply it by c squared. The only difference, how we get the mass defect. In the last question, it was mass of the nucleus, nucleons, subtract them. Here it's the mass of the products, the reactants, subtract them. Otherwise, it's the same question.